Welcome. In this section of the course, we will demonstrate a variety of ways to manipulate and convert a dataset into a time series. Time is the single most important piece of information when dealing with time series, so it's essential to dedicate the next couple of lectures to transforming this data frame in the appropriate type. Let's get started. To begin with, let's transform the date column into a date type. We can start by calling the describe method on the whole data frame to find how long the entire time period is. However, since the date column is not numeric, Python doesn't include it in the summarized statistics. The values are simply a text representation. As users, we can easily interpret those, but Python can't. This poses an issue because we want the option to analyze specific consecutive intervals of time. One way to work around this is to ask Python to describe only the date attribute of the pandas data frame. We accomplish it by writing df_comp.date.describe and running the cell. You will notice that the summarized statistics for dates are very limited and do not include the first or last value in the series. The top date is misleading, as it doesn't hold the highest value or the date with the highest frequency. Instead, it is completely arbitrary. Let me explain. For Python, all the values in the date column are ones because they hold some value different from 0. Therefore, any single date holds a top value. This shows why the method just randomly selects which one to display. We need to fix this if we want to analyze consecutive chunks of data and refer to the values assigned to a specific day. To do so, we must convert the dates into a datetime type. Lucky for us, the pandas package provides a simple toDateTime method we can call. toDateTime requires a single argument, the attribute we wish to transform into a datetime type. In our case, that's the entire date column of the date frame. So we write pd.to_datetime and add df_comp.date in the parenthesis. A specific feature of the toDateTime method is that it assumes we are plugging in a string in a month, day, year form. As you can notice, our data is saved in the day, month, year format, so we need to specify this when calling the method. And we do it by setting the value of the optional argument dateFirst to true. The new datetime values will be recorded in a year, month, day format. Although we're not used to seeing dates like this, it is the most convenient representation, as we can clearly see how the values are ordered. Since we want to replace the string values in the column with datetime values, we need to assign the results to the date attribute of the data frame. If we omit to store them, the code will only display how the column would look, without actually overwriting the data. Therefore, to record the new date type values, we insert the following at the beginning of the line. df_comp.date equals. Great. Now that we have taken care of this, we can run the cell. Now, to make sure we have successfully converted the dates, use the head method to explore the top observations in the data frame. Okay, we see that the values are formatted differently than before, right? To test if the date column is no longer stored as text, we can once again use the describe method. Remember to only call the method on the dates attribute, rather than the entire data frame. Observe how, after the change, we get the more detailed statistics about the time period. We see that it starts on the 7th of January 1994 and ends on the 29th of January 2018. In addition, notice how all the datetime values also include the hours, minutes, and seconds, even though the dataset only holds daily values. That is because Pandas is equipped to handle high-frequency data with differences between intervals as small as a second. Fantastic! Now that we have transformed the date column into the appropriate type, we can use it as an index for our time series. In the next video, we will show you how to set any attribute within a data frame as an index reference. See you there! Welcome back. In this lesson, we will show you how to set any attribute of a data frame as an index. Let's get started. To refer to a set of values as a time series, each one should correspond to a time period. This is crucial for referring to values according to the day they were recorded. Moreover, we often wish to examine specific chunks of data between two concrete dates. For example, analysis of the Great Recession usually involves separating the data before and after September 15, 2008, the day Lehman Brothers filed for bankruptcy. Thus, we need to use the associated time periods as indices. In this instance, we have a data set of daily values. Therefore, each date would be a separate time period, so we can use the date column for the data frame as the new index column. To achieve this easily, the Pandas package provides a method called setIndex. Since we are setting the indices for the entire data frame, we write df_comp.set_index in parentheses. We write the names of the data frame attribute we intend to use as an index from now on. But make sure to put it in quotation marks too. Then we set the value of the optional argument in place equal to true to tell Python to save this new data frame in the place of one with integer indexes. Okay, to see if we've successfully created a time series, let's check the values of the data frame using the head method. Observe how there is no longer a column with integer values on the left. Instead, we have the date column in its place. We can tell these are the new index values because they appear in bold once the data frame is displayed. Now, to see a summary of the date values, we can try calling the describe method for the associated attribute of the data frame. However, when we do that, we get an error message stating the data frame object has no attribute date. Fortunately, there's an explanation for that. Once we turn the date column into an index, we no longer save its values as a separate attribute in the data frame. Now that we've made that clear, note that the indexes are pretty much fixed, in the sense that we cannot freely overwrite them. Therefore, it is crucial to ensure all the indexes are correct. Okay, moving on to the next topic. Time series data requires having a constant frequency that persists throughout the set. In the next lecture, we will show you how to define this frequency for a data set. Thanks for watching. Hello again. In this short lecture, we will show you how to set the frequency of a data set to turn it into a time series. The good news is, the Pandas allows us to assign the frequency of the set by calling the asFreq method. It requires defining a single argument depending on the type of data we are using. The values this argument can take are specific letters of the alphabet put into single quotation marks. For instance, writing the letter H in parentheses will indicate the data is recorded hourly. Most of the possible values are just as intuitive, with W representing weekly data, D daily, M monthly, and so on. Note that the data measured once a year is most often referred to as annual rather than yearly, so the parameter value we use is A instead of Y. Great job so far. Let's continue. Our data contains daily closing prices, so we use the asFreq method to assign the appropriate frequency. Since asFreq is a method, we add parentheses at the end. Now take a look at the first few elements of the dataset using the head method. We see two new periods for January 8th and 9th, which have missing values. That's because these dates were not included in the original set. This means we generated new periods which do not have values associated with them. We will learn how to take care of such issues by the end of this section. Right. Another peculiarity of our data is that it represents the closing prices of financial indices. These prices can only be recorded during working days, so we're not interested in any weekends or holidays. If we do a quick check, we find that the two periods generated by the method are indeed Saturday and Sunday, so we'd better avoid adding such irrelevant time periods into our dataset. Fortunately, the asFreq parameter also accepts the value b, which states the data was only recorded on business days. Let's adjust the argument value and once again call the head method. As you can see, setting the frequency to business days avoids adding many unnecessary time periods. Fantastic! In the next lesson, we will go through the most common approaches to account for missing values. Thanks for watching. Hello. In this lecture, we will introduce several ways of filling out missing values in a data set. For starters, we need to test if assigning the frequency resulted in additional time periods for which data is not available. Again, there's a dedicated method, isNA, which we call on the entire data frame. You will see either true or false for every entry in the set, depending on whether there is missing data for that period. To clarify, true indicates there are missing values, and false suggests there aren't. All right, the bigger the data set, the more difficult it becomes to spot missing entries. Since true is equivalent to 1 and false is equivalent to 0, we can add up the values in each column to determine the number of missing observations. For convenience, we can call the sum method along with isNA. For each attribute, this will determine the number of instances without available information. After running the cell, we see there are exactly 8 missing values for each of the market indexes. Recall that we had no missing values when we first examined the dataset. Therefore, setting the frequency to business days must have generated 8 dates for which we have no data available. All right. To amend this, we need to fill these missing elements with values. The easiest way to do it is via the fillNA method. Let's explain how it works. The fillNA method goes through the entire time series and fills out missing values in several different ways. The first one is called front filling, and it assigns the value of the previous period. For instance, if we have no data available for the 15th of July 2004, we assign to it the value recorded on the 14th of July 2004. The second way we can tackle missing values is called backfilling. As you can probably guess, it assigns empty entries the value for the next period. For instance, if we have no data for July 7th, 2004, we pass it the same value as the one we have recorded for July 8th, the same year. A third way we deal with missing data is by assigning the same value to all of the NA time periods. For instance, it is common practice to assign the average value of the time series to all the missing values. Depending on your data, you may opt for only one or a combination of methods. Usually, filling missing values with the mean is a bad approach when it comes to time series because there are underlying time variant patterns in the data. This approach is appropriate only when the data heavily fluctuates around the mean from the first to the last day. Right. Since we have several time series, we can try out different approaches for filling their missing values. Suppose we want to front fill the missing values for the S&P 500. We would call the fillNA method for the SPX attribute of the data frame. Then, in parentheses, we set the method argument equal to ffill in quotation marks. Before we run the cell, we must assign the completed time series to the original column of the data frame. It's good practice to test if your code works as intended, especially when trying something for the first time. To check that, use the isNA and sum methods from earlier to see how many missing observations we have for each time series. Evidently, there are 0 instances of non-available information for the S&P, while the rest of the time series still have missing values. Okay, what if we want to backfill the FTSE values? Well, the code to execute this is very similar. The only thing we must change is the data frame attribute from SPX to FTSE, and the method parameter from FFill to BFill. Good to go. Now, let's check the number of missing values once again. As expected, there are no longer any missing values for the FTSE or for the S&P. Finally, we're going to use average values to fill out the DAX. Unlike front filling or back filling, assigning the same value to all the missing observations does not require defining the method argument. Instead, it requires passing a number or expression to the value argument. Since we want to set all missing values to equal the average, we need to call the mean method. More precisely, we need to set the value parameter to equal whatever the mean method outputs. To do so, in the parenthesis of the fillNA method, we need to type in value equals df_comp dot dax dot mean, followed by parenthesis. Let's see if our code worked as intended. Since Nikkei is the only series with missing values, we have successfully accounted for NA periods in the other 3 time series. You can fill out the remaining Nikkei values any way you prefer. Great! Since we often analyze time series one at a time, the next lesson will show you how to get rid of supplementary data. Thanks for watching. Welcome. In this lecture, we will see how to add or remove columns of a Python data frame. In time series analysis, we often end up analyzing a single sequence on its own. We will be analyzing how the S&P 500 performs, so we won't be that interested in the other time series. We can remove the columns for the FTSE, DAX, and Nikkei for 2 main reasons. The first one is that the less data we load, the faster we manipulate the entire data frame. This may not be a huge problem for this specific dataset. After all, we only have a little over 6,000 time periods. However, it can significantly affect high-frequency data with hundreds of thousands of observations. The second reason to remove them is for the sake of clarity. Dropping the 4 columns makes it easier to keep track of any new series we might add to the dataset. In analysis, we often keep copies of any major modifications to the data. Therefore, we can expect to have additional columns in our dataset as we analyze the results. Okay, before we remove any data from the set, let's first create a column called Market Value. We will assign this column with the same values as the S&P. This column makes things much more convenient. It allows us, by changing a single line, to reuse the entire code to analyze a different time series. We create this additional column by writing the name of the data frame, followed by the name of the new time series in squared brackets. Since it is a name, remember to put it in quotation marks. As we already mentioned, we set it equal to the S&P, so we add equals df_comp.spx. We can call the describe method for the entire data frame to make sure the new column was created successfully. Since it holds the same values as the S&P, the summarized statistics for the two are identical. Great job! Now to delete a specific column from a data frame, we need to use the del command. We already have a market value attribute within the data frame, so we can remove the 4 original columns. Suppose we want to remove the S&P values first. We write the command del, followed by the name of the data frame. Then inside square brackets, we type the name of the column in quotation marks. If we call the describe method, we see that the data frame no longer contains a column called SPX or any of its values. Right. To remove the time series for the other market indices, we only need to adjust the name of the columns within quotation marks. Instead of SPX, we need to write DAX, FTSE, and Nikkei. In fact, we can do all of that at once by writing DEL df underscore comp DAX, comma, df underscore comp FTSE, comma, df underscore comp Nikkei. Calling the describe method again, we see that we have a single column left in the dataset. It is called market values and represents the closing prices for the index we decided to analyze, which is the S&P in our case. With that, most of our preliminary pre-processing is done. Thanks for watching, and see you in the next lesson. Welcome back. In this lesson, we'll talk about the splitting up of data. To conduct successful machine learning, we need to split our available data into two sets, a training set and a testing set. The goal is to have the option of feeding new information into the model and comparing its predictions to actual values. The closer the forecasts match the actual values, the better our model performs. For many different ML methods, we would shuffle the data before splitting it to make both sets equally representative. However, time series data relies on keeping the chronological order of the values within the set. This, unfortunately, makes shuffling impossible. Okay, since we can't shuffle our data, the testing and the training sets would also have to be uninterrupted sequences of values. Therefore, the training set should include all values from the beginning of the data up to a specific point in time, while the testing set, the rest. The appropriate size of the training set is debatable. If it's too large, the model will fit the training set too well and will perform poorly with the new data. If it's too small, we won't be able to create a model accurate enough. For the purposes of this course, an 80-20 split between the training and testing set is reasonable. Let's begin. To split the data, we need to use the ILOC method, which slices the data. To successfully implement it, we must know where the first set finishes and the second one begins. In other words, we must determine the cutoff point between the two. To achieve this, we will make use of the len function, which returns the length of an object in Python. Let's define an integer variable called size, which depicts how long the training set should be. As stated before, we want to use approximately 80% of the entire data. So we find the length of the entire set and take 80% of that. The result will be the length of the training set. Now we achieve this by writing the following. Size equals int, open parentheses, len, open parentheses, df comp, close parentheses, times 0.8, close parentheses. Notice that the int function ensures that size will be an integer, which serves as an approximation of the 80% cutoff point for the dataset. After determining where the train should end and the test should begin, we can use the ILOC method. Both sets are going to be data frame objects, so we can name them df and df test, respectively. Convenience dictates we call the training set df train, but since this is the data frame we will be using for the majority of the course, we opt for the shorter df instead. Therefore, we assign to df all the values from the beginning of the dataset up to the size value. We do so by typing df equals dfcomp.iloc, ranging from the start of the data up to size. Similarly, we assign the rest of the data to dftest. This time, however, we start from size and include all of the values until the end of the data frame. Great job! To make sure we do not have overlapping values, we can implement the tail and head methods and compare the last elements of the training set with the first elements of the testing set. Since the first set ends on 5th of April 2013, while the second one starts on the 8th, there is no overlap. The 6th and 7th were not business days, so they are not present. Splendid work! After successfully pre-processing the data, we can begin the modeling part of our analysis. In the next section, we will discuss the main approaches for mathematical modeling. Thanks for watching.